Okay. Okay, I'm going to talk now about solutions. Start talking about solutions. Actually, no, I'm not. I'm wasting something I forgot from last week. Just the, what section would that have been? Somewhere I talked up to section equations 52, 53, 54, 55. These are the equations dg dt is minus s, or dg over t. d1 over t is h. Those are called the Gibbs Helmholtz equations. Just the name, that's all. Equations 52 to 56, all of them are forms of the Gibbs Helmholtz equation. Probably better didn't say that last week. Okay, I want to talk about ideal solutions, and ideal solutions are discussed in section 4.1.5, or 4.1.5 talks about ideal solutions. Or I also have ideal solutions. The one I'm going to use is same thing. You can look at any one you want. But up here I have ideal solutions number 3. Okay, so that's about ideal solutions. Okay, so the definition of ideal solution. In an ideal solution, we're assuming that it's an ideal solution of two molecules, A and B. So we have a random distribution of Na molecules of A and Nb molecules of B on Na plus Nb lattice sites. So here we can imagine we got some sort of a these are my lattice sites. So these are the lattice sites, and I'm distributing A and B particles completely randomly over the lattice sites. Okay, so our ideal solution has a random distribution. This is the essence of an ideal solution. The solution is random. That means the probability, if I put the probability of an A being here is independent of what's around it, independent of its neighbors. This is because A and B are then, we assume, extremely similar chemically. In the limit, you would have, say, the most ideal solution would be a mixture of two isotopes of the same element, but two elements that are very similar chemically are going to be close to ideal. They'll be randomly mixed. For the same reason that they're randomly mixed is that they're very similar. This means the enthalpy of mixing is going to be 0. You mix A and B, basically the bond energy, an AB bond, an AA bond, a BB bond all have the same energy. So when you mix them, there's no change in energy. And they're going to be randomly mixed because, again, all the bonds have the same energy, then A and B don't try to get next to anything particular to lower their energy. Okay, so given those assumptions, how are we going to calculate the entropy? We're going to use Boltzmann's equation. S is K log. That was a different notation. You go way back. S is K log T. T was the multiplicity. Here we use omega for the multiplicity as just another symbol, but T is the number of arrangements. So Boltzmann's equation. Here Patrice wrote omega because some people do that. T is the multiplicity. K is Boltzmann's constant. Omega is the multiplicity. And so now, since it's completely random, the multiplicity is simply the number of ways of arranging Na particles of A, Nb particles of B over Na plus Nb sites for a random distribution. And that then is equal to Na plus Nb factorial divided by Na factorial Nb factorial. Now we're interested in the entropy of mixing. This is the absolute entropy of the solution. Okay, the entropy of pure A is 0 and the entropy of pure B is 0. This is the configurational entropy. I'm not interested in the vibrational entropies. This should be written configurational entropy. Configurational entropy is the distribution of particles in space. Clearly pure A doesn't have an entropy of 0 unless it's at 0 Kelvin. Okay, but it could have a 0 configurational entropy in this respect simply because every space is occupied by an A. So the multiplicity is 1 and the entropy then is 0. Configurational entropy is 0, the distribution in space, that's all we're concerned about here for the moment. And similarly, the entropy of pure B is 0 because in pure B, every lattice site is occupied by a B. The multiplicity is 1. There's only one way of doing that. Okay, so the delta S, this is the entropy of mixing for the mixing reaction. The mixing reaction would be XA moles of A plus XB moles of B form 1 moles of solution. And this is delta S. Sometimes a little m here for mixing. This is the entropy of mixing, called the integral entropy of mixing, where you take pure A and pure B and mix them to form a solution at a constant temperature. Okay. That's the entropy of mixing. The entropy change when you mix pure A and pure B. The entropy change then is the entropy of the delta S then is the entropy of the product, which is the solution, minus the entropy of the reactants, which are 0 because they're pure A and pure B. So in this case, delta S is equal to S. So now Na and Nb are extremely large. They're of the order of 10 to the 23rd. We're talking about a mole. So we can use Stirling's approximation. Stirling's approximation is just mathematics. Ln, the natural log of factorial n is approximately equal to n ln n minus n if n is very large. Okay, so we can do that mathematical formula. All right, hence delta S is equal to S, so we apply Stirling's approximation into this equation, and so we replace Na plus Nb factorial by Na plus Nb, LaNa plus Nb, minus plus Na plus Nb, and so on. So we just, into this equation here, you use Stirling's approximation, collect terms, and you will end up with this. So that's the entropy of mixing, just by putting Stirling's approximation. But now, Na over Na plus Nb is the mole fraction of A. X is the mole fraction. So the number of atoms divided by the sum of the total number of atoms is the mole fraction. So this ratio here is Na. This ratio here is, Xa. This is Xb. And we let Na plus Nb equal Avogadro's number. So we're taking 1 mole of material. Okay, and then K times Avogadro's number is equal to R. So Boltzmann's constants times Avogadro's number is equal to the ideal gas constant, universal constant. Okay, so in that case, K Na becomes equal to R Xa. Okay, so the entropy of mixing then is minus R Xa log Xa plus Xb log Xb, which is what we're after. This is the equation we're after. This is the entropy, molar entropy of mixing. That's why I have a small s, of mixing Xa moles of A and Xb moles of B to form 1 mole of solution. Now the Xa and Xb are always less than 1, so the logarithms are always negative, so the delta S is always positive. Forming a mixture is you're increasing the disorder of the system. So the delta S is a positive term. I'm going to do this. I'll do this part later. This is the part I wanted to do right now. So that's the entropy of mixing of an ideal solution. The heat of mixing of an ideal solution will be equal to 0 because, well, that's the definition, but the reason is that the bond energies are all assumed to be the same. So delta G of mixing is delta H minus T delta S, which is equal to minus T delta S. So the Gibbs energy of an ideal mixture is completely entropic. There's no enthalpy, it's all an entropic term. Delta S is positive, delta S is positive, so delta G is negative for forming the ideal solution. And that means the delta G is negative, which means the solution is more stable than the pure materials. If you put 2 materials together, they'll form an ideal solution spontaneously. What makes a solution ideal? Well, what makes a solution ideal, I already said, is what makes delta H approximately 0 and what makes the entropy approximately random, and that's if A and B are very similar chemically. Now here I've mixed them on a lattice. This same equation would apply for a liquid, in which case you don't consider this to be a crystal lattice, but you consider the lattice in quotation marks to be the instantaneous sites of the atom. You imagine the lattice that is frozen. You have positions of the atoms, the lattice is frozen, and you then distribute the A and B over the instantaneous positions. Actually, it's the same thing for a gas. I simply imagine, I don't have to have a lattice at all, really. This is just, I could have a gas consisting of A and B. And if at a moment I freeze the gas, I would have, these are the positions at any instant at which I find the molecules. And now if the A's and B's are randomly distributed over those positions, I have an ideal gas mixture. An ideal gas mixture is one that obeys Dalton's law. Okay? Now you might say an ideal gas mixture, we don't talk about ideal gases with delta S as this, but you could arrive at the same equation, just show you how everything hangs together. Supposing you had a let's say we have XA moles of XO2 moles of oxygen over on this side, and over on this side we have XN2 moles of nitrogen. Total pressure is, let's say, 1 atmosphere. Okay. This occupies a certain volume, this occupies a certain volume. Oh, let's make it even simpler. Let's take half a mole of oxygen on this side, and let's take half a mole of nitrogen on this side. Let the pressure be an atmosphere. And now I open up the valve, and they mix. All right. I calculated that the other day. If you remember, what I did was I did it in two parts. I said, since the oxygen and nitrogen don't see each other, there's no interaction between them, we simply assume like the oxygen expands to twice its volume and the nitrogen expands to twice its volume. Okay, so what we have here is we have delta S. We have, say, oxygen occupying a certain volume, then expands to occupy twice the volume. And okay, remember delta S then was equal to minus R log V final over V initial. Sorry, plus R log V final over initial, which will be R log of 2. No. And minus R log 1/2. Minus R log 2, minus R log 1/2, correct. That's the entropy for expanding oxygen from 1/2, from one volume to double the volume. Just R is Q reversible over T. I did that last week, and then this would be delta S of the oxygen with, okay, let's do it all right, let's do that. The delta S of the oxygen, to expand just the way we did it before, the delta S is Q reversible over T. You calculate the reversible heat to expand a half a mole of oxygen to twice its volume at constant temperature. That's the number of moles of oxygen, R log V final over V initial. That's minus 1/2 R log 1/2. The delta S of the nitrogen is also minus 1/2 R log 1/2. So the delta S total is equal to minus R 1/2 log 1/2 plus 1/2 log 1/2, which is exactly the same thing. How's that? Okay, you're mixing half a mole of each to form. But that's not the ideal solution. I'm just trying to show you that you don't have to have a lattice. This is just, everything hangs together, okay? But this is the expression then for mixing. This is from starting with Boltzmann's equation for the entropy. In terms of the multiplicity up here, you end up with the entropy for an ideal mixture. Let's equal to that. Okay. So that's our ideal solution. And I said we should go to, okay. Any questions about that one to start with? Okay, that holds for ideal solid solution, ideal liquid solution, and even an ideal gaseous solution. Now I want to go to the book here and go to section 2.7, which will be on page 22. All right, the chemical potential. Chemical potential was defined in equation 5. All right, we're going to equation 5. Chemical potential was defined in equation 5. All right, you remember in equation 5 I said U is a function of entropy, volume, and number of moles. Those are the extensive properties. You have a system that's at equilibrium. Its internal energy depends on the entropy, it depends on the volume, it depends on the number of moles. Okay? where now, so it's du ds plus du dv dv plus du dn. So mu is, I call the chemical potential, and it's given as the change in U with the number of moles of I as you keep entropy, volume, and the number of moles of everything else constant. Okay, and then it turns out this is the temperature. So du, this turned out to be TdS. This was minus PdV plus sigma mu I dni. Up until now I said let's assume this term is 0 because you have a closed system, so the total number of moles is not changing. Okay, but now we're going to consider the change in, we're going to consider an open system. Okay, so the chemical potential then is given by this equation here. And the chemical potential is the change in internal energy. The change in internal energy as you add a component I, keeping entropy, volume, and J constant. So I imagine I have a system here. We can find a pen that works. I have a system, this is the system, whatever it could be. Into that system I put Na moles of A. So the system contains A, B, C, D, a solution of A, B, C, and D, and so on. A, B, C, D. I add Na moles of A, I keep the temperature constant, I keep the entropy constant, and I keep the number of moles of B constant, the number of moles of C constant, and so on. I simply add a small amount of A, D, and A. Okay, and then there's going to be a change in U because I've added Na and du, dna. Keeping all of these things constant is called the chemical potential of A. So what's the whole point of all that? Alright, so let's go then to page 22. There's got to be a better way of doing this. Alright. So this is not terribly useful because this is du dna, but you're keeping the temperature constant, the entropy constant, and the number of moles of other things constant. And I mean, how do you keep the entropy constant? This is not something that's easy to visualize. Let's try to convert the thing around. So I'm going to substitute equation 11 into 19, differentiate and substituting equation 9. What I'm doing here is I'm taking G is H minus Ts is equal to U plus PV minus Ts. I'm differentiating it. I'm saying dG is then equal to du plus pdV plus vdP minus TdS minus SdT. Okay, and to this then I am substituting, differentiating and substituting equation 9, and I end up with this equation. dG is vdP minus SdT plus sigma mu I dni. Okay, that's just fiddling around with the mathematics. Okay. So, if I keep pressure and temperature constant, then clearly mu I, this is the same mu I, it's just, I'm just making the substitutions. And no, so, okay, so let's write it down. So I make that substitution, equation 9 was du equals T ds plus, or minus P dV plus sigma mu I dni. Okay, so I take this equation, which is just differentiating this. This was the equation we looked at back, equation 9. The definition of mu I, substitute this equation into here, collect terms, and I end up with that equation. And so from this equation you can see that mu I is dG dni at Tp and Nj constant. It's the same mu I, it's just another way of looking at it. Okay, so now what this means is if I take my system, I add dna moles of A, but this time I keep temperature, pressure, and Nb and C and so on constant. And now I'll get dG dna at constant temperature pressure is equal to mu A, and that's a much more useful thing because you can imagine keeping temperature and pressure constant as you add a certain number of moles to your system. So it's the same chemical potential, but this is the most useful way of looking at it. You can also fiddle around, you get dG. So I can show the chemical potential, I'll let you figure these things out yourself, but the chemical, so there's different ways the chemical potential is given by dG dni at Tp constant. It's also given by the original equation, du dna at T and S constant, which is less than useful. If you fiddle around with your equations, you can end up with that equation, and this is an error in the text, which I discovered this morning. This should be mu I, mu A is also equal to dH dna, and I have to correct this, luckily I haven't published it yet, This should not be T and V constant, this should be S and P constant. So if you wanted to keep entropy and pressure constant, that would be another definition of S. Again, not a useful one, mu. Not a useful one, this is an error. This should be S and P. Or you can also show, remember A, we defined A as being equal to U minus TS. Well, the chemical potential is dA at T and V constants. So they're all the same chemical potential, it's all the same thing. Okay, but this is the one that is useful for us. The others are all the same chemical potential, but not highly useful equations. Maybe this one is somewhat useful if you're really doing things at constant volume. But okay, of these the most useful is equation 65. Chemical potential then of the system is increase. The increase in Gibbs energy as the component is added to the system at constant T and P. Okay, the chemical potentials are intensive properties of a system. That is, they're independent of the mass of a system. I think this should be obvious. No matter if I add DNA moles of A to here, the energy, the Gibbs energy will change because I'm adding another material. It's going to integrate itself into the system and form bonds. But I mean, if I add a millionth of a mole to 1 mole, or if I add a millionth of a mole to 1,000 moles, it's going to give me the same change in dG. Okay. As long as the composition of these things don't change, that's why you're adding a small amount. So it's an intensive properties. So chemical potential has units of joules per mole. It's independent of the mass of the system. It depends on the temperature, the pressure, and the composition, of course, but it's independent of the mass of the system. This, of course, only holds it for a system at equilibrium. You're taking a system at equilibrium and you're adding something to it. So why is this property called a chemical potential? This was developed, the whole idea was developed by Gibbs. A potential is a potential gradient is something flows down a potential gradient. So if you have an electrical potential, then electrical charge will flow from high to low potential. If you have a gravitational potential, things mass falls from high to low potential, and so on. So potential. So chemical potential is a potential for the flow. So if you have two systems together, and in one system the chemical potential of A is higher than it is here, then A will flow from system 1 to system 2. Flow means in general, it might react to go to system 2, but if A goes from here to here because it goes from high to low chemical potential. So that's a potential for the transfer of that component. I'll show what it means. So why is it called a chemical potential? By the following thought experiment. Imagine two systems, 1 and 2, at the same temperature and pressure, and they're separated by a membrane that permits only one component, say component 1, to pass from one to the other. So we can imagine now that we have two systems. All right, here's my two systems. Systems 1 and 2. They're both at equilibrium. They're different systems. They're not at equilibrium with each other, but they're two systems at equilibrium internally among themselves. They have several components, A, B, C, D, and here on. And here you have chemical potential of A in system 1 is mu A1, and the chemical potential of A in system 2 is mu A2. Here I said component 1, so let's use component 1. So the chemical potential of component 1, so it's a system of several components, 1, 2, 3, like lead, tin, mercury. Okay, so the chemical potential of 1 is, so let us suppose now that this membrane permits the passage of only component 1. Components 2, 3, 4 can't get through, but component 1 can traverse the membrane. And let us suppose that we observe that dN1 moles of 1 goes this direction. Okay? Okay, so we have here the chemical potential of component 1 in compartment 1 is dG1dN1, and the chemical potential of component 1 in compartment 2 is dG2dN2. Component 1 is transferred across the membrane with dN1 is obviously equal to minus dN2. So dN of 1 in compartment 1 is minus dN. It leaves here, goes to here. So if this is dn1 and component 2 is positive, then it's negative over here. It's transferred. Okay, transferring from 1 to 2. So the change in total Gibbs energy, then, the total Gibbs energy change will be dg of compartment 1 plus dg of compartment 2. dg of compartment 1 is mu1. The Gibbs energy, the change in Gibbs energy of compartment 2 is dg2 dn2 times dn2. Okay, the Gibbs energy change in compartment 2 is equal to dg of 2 dn2 times dn1. Okay, these guys. Sorry, dg2. So this is equal to mu of 1 in component 2 times. Okay, that's the Gibbs energy change for compartment 2. dg dn times dn. Okay, so the Gibbs energy change in compartment 2 is mu1 in compartment 2 dn1. Compartment 2, the Gibbs energy change of 1 is mu1 and 1 dn1 and 1, which is minus dn1 and 2. Okay, let's suppose that the chemical potential of 1, let's just suppose that the chemical potential in compartment 1 is greater than the chemical potential in compartment 2. In that case, this term in parentheses is positive, and the total Gibbs energy change is negative, so it's a spontaneous process. Okay, so if you have two compartments with a different chemical potential of component 1 in the two compartments, with mu1 and 1 greater than mu1 and 2, and you transfer component 1 in that direction, there's a decrease in Gibbs energy, so that's your spontaneous process. So 1 will be spontaneously transferred from high chemical potential to low chemical potential. So mu1 is a potential for the transfer of a component. Component A always moves from high potential to low potential. So that's at constant temperature and pressure, but I showed up here that there are different things. If you could do exactly the same thing for a transfer at constant temperature and volume, and just do exactly the same argument but use dA. This is the same chemical potential, so you get the same thing. If the transfer is at constant temperature and volume, you will also get a spontaneous transfer. If you did it with the U at constant entropy and pressure, constant entropy and temperature, whatever, you'll get the spontaneous transfer. So it doesn't really matter what you keep constant. So it truly is a potential. It's not just at constant T and P, it's no matter how you do it, you're going to get it. That's a true chemical potential independent of other stuff. So you have a potential for each component of your solution, and that determines which way the thing will go. And the system, if the chemical, for two systems to be in equilibrium, the chemical potential of every component for this, the chemical potentials have to be equal in the two compartments for each component. Mu1 here has to be equal to mu1 here, mu2 here has to be equal to mu2 here, and so on, otherwise the system's not in equilibrium. Just as the temperatures have to be equal, the pressures have to be equal, the chemical potentials have to be all equal if two systems are truly in equilibrium. All potential, now in that case, all potentials are the same temperature as a thermal potential. That's a potential for the transfer of heat. Pressure is a mechanical potential. It's a potential for the transfer of volume. If pressures are different, you had a piston here, it would move. Okay, so your mechanical potentials, your thermal potential, and all your chemical potentials all have to be equal in both systems before the system's truly at equilibrium.
The bracket will be here.
Sorry?
The bracket position here. If D will be inside the bracket.
Sorry?
If this D will be inside the bracket.
Oh, you're right. Thank you. Ah, another error. Damn it. You know, you read the thing over 100 times. Should be enough there.
Both of them. Two lines.
Well, dg1 plus g2, or you can put it both inside or both outside, but one or the other. Up here too. Oh, sorry. See what you mean. Right. Okay, thank you. All right. Well, they haven't published it yet. I haven't seen the proofs yet. It's 2 errors on the 1 page. I got it. You know, you read it over 5 times. Back when I did my master's, I wrote my first paper ever. I won't tell you what year it was. And I read the thing, it was my first paper I ever wrote, and I read the thing over 8 times to be sure it was perfect, and then when it finally came out in the journal, I went down to the library and read it on the very first equation, on the very first page. There was an error. Equation 1 on the page 1 of the first article I ever wrote had an error in it. So, sign wrong. Anyway, okay. So, this is what I said. When 2 or more phases are in equilibrium, the chemical potential of any component is the same in all phases. And again, this is equivalent to minimizing the Gibbs, total Gibbs energy of the system. It's all the same thing. Okay, so in fact, Sage, the algorithm does not explicitly try to get the chemical potentials equal, but minimizing the Gibbs energy comes out to exactly the same thing. I'll show you. Now I'm going to go to now we'll talk about partial properties in general, and that's this number 4 here. Oh, beautiful. Okay. I'm going to talk now about the whole definition of integral properties, partial properties, and so on. This is because you're dealing with these things all the time. Well, now you know exactly what chemical potential is, but let's talk about partial and integral properties and so on in general. And we can talk about any property, any extensive property, such as H, S, G, and also volume. And I'm starting off with everything I say here for volume applies to every other letter of the alphabet. The reason I'm starting with volume is because I think it's just a little bit easier to visualize. When you start talking about partial enthalpies and partial Gibbs energies, it's a little harder to visualize than the partial volumes. I'm going to talk about partial volume, and then we just generalize it later. So, first of all, so you all have this. So this is the, actually some of this, well no, this is not really in the book. Okay, this reaction here, which I showed earlier, this was the reaction when we mix something. This was the mixing, the integral mixing reaction. I did that for delta S. Okay, but this is your integral mixing reaction. XA moles of pure A plus XB moles of pure B forms 1 mole of a solution at constant temperature. That's called the integral reaction of mixing. You're taking pure A and pure B and you're mixing them, and the temperature is constant. Okay, and for that we use the symbol, so the change in volume of that is delta V, which is a small v because it's a molar property, you're forming a mole. If you had several moles, it would be delta capital V. Okay, now sometimes you'll put a little m up here for mixing, delta V of mixing, but people get that confused with melting, and I think it's just too many symbols, so let's just call it delta V. Isothermal, and that's called the integral molar. Integral because it's a pure A and pure B, it's not a partial. Integral as opposed to a partial, which I'll define in a minute. Integral molar volume of mixing is the proper term for that property. Okay, so here, so that's the molar property. And that's the molar volume is equal to the total volume. This is volume, this is liters per mole, this is liters divided by the total number of moles. Okay, Na and Nb are the total number of moles of A and B. So this is the molar property. We now define the partial molar volume. Is defined very similarly to the way we did the chemical potential. Okay, we take the we take a system here at equilibrium, which is at a certain temperature, pressure, number of moles of A, number of moles of B, and whatever. And to that we add D and I moles of component I at constant temperature and pressure. And the partial molar volume of I is defined as the change in the volume, the total volume in liters, D and I at constant Tp and Nj. Okay, it's exactly the same thing as mu I was defined as dg dni at constant temperature, pressure, and Nj does not equal I. Partial molar volume is defined the same way. Okay, the partial molar enthalpy is defined the same way. You would have H partial enthalpy of I is dH, dNi at Tp and Nj, and du, ds, dg, whatever. Okay, same thing. Clearly, mu I could also be dgi, could also be defined as then, by this same sort of thing, is gi. In fact, the partial, this is the partial molar Gibbs energy, is exactly the same thing as the chemical potential. Same thing. They're equivalent. Okay, just another symbol for the same thing. All right, anyway, let's go back to the volume. The volume, okay, here I'm plotting now the volume. This is the volume of the solution, the molar volume in cubic centimeters per mole, versus the mole fraction of B, going from pure A over here to pure B over here. Okay. This then is, this point here is V naught of A, so this is the standard molar volume of component A. Standard because it's pure A. Molar because it's per mole. So V naught A is this point. This is the molar volume of pure B. It's the standard, okay? And this then is, let's say, the volume of the solution which you observe. Okay, the solution is miscible at all compositions. We can mix them like water and alcohol are miscible at all compositions. And this is the V. This curve is V. So this distance is delta V according to this, okay? XAA plus XBB, the reactants here, XAA plus XBB, that's simply the equation of this straight line. Okay, so the molar volume, delta V is equal to V minus, okay, here we go, delta V, he didn't write that out, so I'm going to write that out. If that's delta V, then delta V is equal to V of the solution minus XA V naught A plus XB V naught B. Okay, the delta V is the V of the products minus the V of the reactants, which gives you that equation. D'accord? All right, so that method. Okay. So this line here, this curve here is V. This line here is XAVA plus XB, so this is delta V here. In this particular case, we see that delta V is negative, which means that the volume of the solution is less than the linear combination of the volumes of the pure materials in this particular solution that I drew, hypothetical solution. It doesn't have to be, it could be positive. You could actually have a delta V that went up like this. Or you could have a delta V that went along here, okay? The majority of solutions that you observe in reality have a negative delta V. Negative delta V means if I start with a liter of water and I start with a liter of alcohol and I mix them, the total volume is less than 2 liters. That's what happens here. Otherwise you'd be on the straight line. So that's called a negative delta V. Most solutions have negative delta V's or slightly negative. Some have positive, most have negative. The reason being simply that if you mix things together, they can sneak into the holes in between. If you take a bunch of large balls and a bunch of small balls and you mix them together, the small balls can sort of fit into the holes with the big balls. They pack more densely and the total volume is lower. Okay. However, in some materials you would get a positive because the bonding changes and so on. But it can be positive or negative, it's usually negative. Okay, so if I define V this way, VI, partial molar volume, is defined that way. Simply the change in molar volume is the number of moles of I increase. So dV, then, this is just calculus, the change in molar. If I added Na moles of A and Nb moles of B at the same time, the total change in volume would be VA dNA plus VB dNb. Okay. If I divide now by Na plus Nb, then the total, this becomes molar, and the dNA becomes dXA. Okay, I'm just dividing through here. I'm just taking, this is just calculus. If I add A and B simultaneously, I get this. Dividing through by Na plus Nb, I would get this. Okay? Because big V over Na plus Nb is little v, and Na over Na plus Nb is Xa. Mole fraction. Now, I go from this to this. where I've simply taken away the differentials. And this is not totally evident. So I'm going to take this equation here. dV is XA dVA plus XB dVB. I was trying to give you an idea of this, what all this means, the mathematics and the thought experiment. Let's suppose that I'm going to integrate each side like this, and I'm going to go from 0 to V. And this is going, sorry, XA. Let me start with, better to start with this one. Makes more sense. You can't really add XA home. Let's start with this one, D. Big V is partial molar volume of A dNA plus the partial molar volume of V dNB. Okay. That's just math. From this definition here, that's just the fundamental equation of differential calculus. We're going to integrate each side. And I integrate this from 0 to V, I integrate this from 0 to NA, and I integrate this from 0 to NB. What does this mean physically? You can imagine here I have an open system. Here's my system, and the system has a volume. The system is initially empty, so the system initially has nothing in it. And let's say here I take another beaker, and this contains AB solution. It contains an AB solution at fixed composition. Okay, AB solution containing Na moles of A and Nb moles of B. Alright, and I pour this solution into here, and I fill up, and the volume is V. So I take a ready mix solution, and at constant composition, I add it to the system, and I fill up the system. So it's an open system. Okay, so that's what I'm doing here. The system starts with 0 volume, and after I pour the whole thing in there, it ends up with a volume of V. The total number of moles of A goes from 0 to Na, and the total number of moles of B goes from 0 to Nb. And it does this at constant temperature, pressure, and composition are constants. D'accord? Now here's the important thing, that VA and VB then are constant during this process. VA and VB, the partial molar volumes depend only on temperature, pressure, and composition. They're intensive properties of the system. Okay, so the partial molar properties of this solution are VA and VB, and since TP and composition are constant, I'm doing the addition at constant molar volumes. Okay, so I can take the molar volumes outside the integral signs, and then integrating this with the molar volumes outside the integral sign gives me that. Okay, so I get V equals VANA plus VB NB. Okay, so the total volume is equal to the weighted sum of the partial molar volumes by integrating the differential equation because the partial molar volumes are constant, intensive properties. Now I can divide this equation through by the total number of moles, and that would give me this equation. You take this equation, you simply put it on a molar basis, you divide by Na plus Nb, so you get the molar volume is Va times Xa plus Vb times Xb. So this is the integral, this is called the molar volume, and this Va is the partial molar volume. So the total volume is equal to the weighted sum of the partial volumes. And that's why they call it the partial volume. That's the partial volume of A, that's the partial volume of B, and this is the total volume. This is a very bad term because there's no way that you can say part of the volume is occupied by A and part of the volume is occupied by B. The total volume of the system depends upon the way the A and B's go together. So there's no way whatsoever you can say part of the volume is occupied by A and part of the volume is occupied by B. And the reason I start with the molar volume, one of the reasons is that to show how ridiculous this is, you can imagine a partial molar volume which is in fact 0. Let us suppose you have a system like iron carbon is almost zero. If you take iron, a big, carbon is small, you put the carbon in, it goes into the interstices. So as you add carbon to iron, the molar volume doesn't change. Okay, so the partial molar volume of carbon is zero. So the part of the volume by carbon is zero. Now you can get more than that. Supposing that you put in something like carbon, I don't think this is quite the case, but let's suppose that you have a lattice of some metal, M, and into that lattice you put a small nonmetal like carbon. So first of all it goes into the interstices, so it doesn't expand the lattice at all. And you form very strong bonds here. So what it actually does is it pulls it in a little bit. Now what happens is you're going to get a negative partial molar volume. Okay, so you're going to add this material to your metal, and you're going to find there's actually a decrease in the total volume. Okay, so you have a negative partial molar volume, and of course then trying to say that that's the part of the volume is ridiculous. You can't have a negative part of the volume. So this is really, but this is the name. The reason they call it partial molar volume is you look at this and, well, that's the part of A and that's the part U to B. But don't think of it as part, just think of it as. Okay, so in molar volume you can actually have a negative partial molar volume. It's rare, but it observed. You can certainly have one very close to zero. Although usually the partial molar volume is positive. Another term which we have here then is this term. This is delta VI, which is VI minus V0I. And this is called the relative partial molar volume of I. So the partial molar volume of I, remember, this varies with composition. VI changes with composition. Okay, VI will change with composition. So delta VI is VI minus the standard state I. So this is called the relative partial molar volume of I, or sometimes the partial molar volume of mixing. This is the integral molar volume of mixing, delta V. This is the partial molar volume of mixing, or the relative volume. And if you make the substitutions, delta V, the integral delta V, is the weighted sum of the partial delta V's. Now, we have so in delta V then, now, okay, so going back to here now, looking at this diagram, we have what we call the tangent construction. If you take a composition, here we have 60%. I think I have that on the next page. No, I don't. Here you have a composition of a system at 60%. So this is the delta V. Here you have 60%. I draw a tangent to this curve at 60%. And I extend the tangent line to the two ends. Mathematically, this point here, this intersection point here, is the partial molar volume of A at this composition. And this intersection point here is the partial molar volume of B at this composition. I'll prove that in a moment. So then this distance here then is delta VB. Delta V is V minus V naught. So this distance is delta VB. And this distance here is delta VA. Delta V is negative, so delta VB is negative, delta VA is negative. Okay, now why does this tangent construction work? Why, when I draw the equilibrium, when I draw the tangent at 60%, this point then is VA at 60%, and this point here is VB at 60%. This comes from two equations. It comes first of all, two equations have to be satisfied. This equation and this equation. These two equations here have to be satisfied. So this line here then satisfies clearly this equation. This point here is the molar volume at 60%. And so VA, if this is correct, this construction I did satisfies this equation. VAXA plus VBXB is the equation of that straight line, and that's equal to V at that point. Okay, so clearly that construction, if that's in fact VA and that's VB, then the construction satisfies that equation. Okay, now does it satisfy this equation? So dV is VA dXA plus VB dXB. Let me integrate that equation. So dV is VA dXA plus VB dXB. dXA is equal to minus dXB, for sure. XA is 1 minus XB. Okay, so dV is equal to VB minus VA dxb. I integrate that both ways, and I get delta v equals to vb minus va times the integral of dxb, which is equal to 1. Okay, so delta v is equal to vb minus va. Okay, but this distance here then is vb minus va is equal to, what am I doing here? That's all wrong. I'm sleepy today. What did I do wrong? No, that's all right. I thought not dealt with it. Just, didn't sleep enough last night. Half asleep. Go back to here. This equation dxa minus xb, so we have dv dxb is equal to vb minus va. Okay, dv dxb is the slope of that straight line. Okay, dv dxb, that's the slope of the line, it's a tangent line, so it's the slope is dv dxa at that composition, and that's equal to vb minus va divided by this distance here is 1. Okay, so the first equation here, v is xa va plus xb. This equation says that this straight line goes through that point. This equation here, which is this equation here, says that the slope of the line, that the line is a tangent point. That's all. So that's your mathematics. So this is points. So you see, as you rotate a tangent around here, then VB minus the VA will change and VB will change depending upon the composition. That's called the tangent construction. Okay, so there are your partial molar properties for the volume, which is kind of something you can understand. And as I drew this, actually now you can see that if I were to draw this tangent at a high enough, this is the way I drew this particular thing, you could actually end up with a partial molar volume which was negative. Even though the volume's always positive, but you got a negative enough deviation, you could actually have a place where the partial molar volume went negative. It's unusual for that to happen, but it can happen. Okay, now, okay, so that shows everything. Integral molar volume of mixing, partial molar volume of mixing, and so on. If we go to the next slide, this delta V, what we often do then is we put this VA0 and VB0 at 0. We put everything relative to the pure material, so I'm just plotting delta V now. And if you plot delta V, it's the same line, just with this, just with the two ends of this line put to, this point put to 0 and this point put to 0, so you end up with delta V. And now, of course, then this intercept is delta VA, which is this distance, and this intercept is delta VB. So it's usually done that way. And then these two equations are done. Now you can imagine then you have a tangent that rotates around this line. So imagine I start here with a tangent, and I rotate the tangent around that line. You can see this point here then decreases. The point here at pure A, this delta VA is 0, obviously, and then it becomes more negative. Okay, and delta VB will start off here and become more negative as well. So if I were to plot now, these delta VA is this distance, delta VB is this distance, and I was to plot these two partial molar volumes of mixing as a function of composition as we rotate the tangent around the material. You don't get it here. Okay. Then what you would get here, I'm going to plot delta V of I going from A to B. Okay, so now I'm rotating the tangent around, and so delta VA is going to look like this. This is going to be the curve of delta VA, and this will be the curve of delta VB as a function of composition, starting at 0. Okay. Starts at 0, of course, because delta VA is VA minus V naught A. If you're at pure A, then VA is V naught A. So Okay, any problems with that? This point here is finite. This doesn't go down to minus infinity. It's a finite value because the limiting slope here is not, limiting slope is not vertical. The limiting slope has a finite value. So if you take the limiting slope and you extend it down to this axis, that would be this point here, the delta VB in pure A, which is obvious. You're taking pure A and you're adding some B to it. That's the volume change, it's not infinite. Any problems with that so far? All right, now we can do that for other letters of the alphabet, so let's do it for H. So now we can imagine we're here. All right, and just everywhere here you see a V, put in an H. All right, so here you've got delta H. So this is the integral enthalpy of mixing. So if I take pure A, pure B, and form a mole of solution, delta H is the heat that's given off. So it could be negative or positive or zero. Okay? You could have an exothermic, endothermic, or in an ideal solution it would be zero. You could have an endothermic or exothermic. Okay, the partial molar enthalpy would be small hi, which is dH dNi. It's the change in the enthalpy as you change the number of moles. All of these equations apply, except everywhere you see a V, you put in an H. I could then plot here, I could plot H. This would be the molar enthalpy, H in joules per mole. And that would go from H0 of A to H0 of B, and this distance would be delta H. This would be H of A at this point. This would be the partial enthalpy of B at the point. Exactly the same thing. This is delta H of B. This distance is delta H of A. Same thing. Just replace V's by A, and this becomes joules per mole. Integral enthalpy of mixing, partial enthalpy of mixing. If I were to plot it on this graph, now this is more. The thing is, with the volume, you can actually plot. It makes sense in the volume. You can actually define an absolute volume in centimeters cubed per mole, because you have a real zero. The real zero is no volume. Okay, but with enthalpy, the volume is, enthalpy is with respect to an arbitrary zero. So in the enthalpy, it probably makes more sense to plot delta H. So this is the enthalpy of mixing, the molar enthalpy of mixing of A and B to form 1 mole of solution. So this is the enthalpy you would get. If this is negative, then you have an exothermic mixing. Positive, you have an endothermic mixing. If it's zero, you have an ideal mixing. The tangent construction applies, so this would be the partial enthalpy of mixing of A at that composition there, and this is the partial enthalpy of B at that composition. And if I were to plot going from A to B, I were to plot the partial enthalpies. Well, then the partial enthalpy of B would look like that, and the partial enthalpy of A would look like that, and the integral enthalpy looks like that. Okay, so that's what integral enthalpy is like. You can do the same thing with entropy, internal energy, or anything you want, but more specifically, you can do the same thing with Gibbs energy. Okay, so I'm doing exactly the same thing now, but instead of V, I write G. Okay, so this is the molar, this is the Gibbs, integral molar Gibbs energy of mixing. Taking the integral, it's not the partial, you're taking the whole, pure A, pure B, and you're mixing them a constant T. So that's the integral molar Gibbs energy of mixing. And the molar is equal to the total in joules over total number of moles. The partial molar Gibbs energy of I is dG dNi, and this is also known as chemical potential. Okay, GI. In this chapter here, I talk a little bit about GI, but mainly I use μI now. This is chemical potential. That's why the G is, of course, the partial properties here are very important because of this prime importance of the chemical potential as a potential for transfer of A. And you have very important equations, but they're exactly the same as with the volume, except so dG is GA dNA plus GB dNB, or dG is mu A dNA plus mu B dNB. Every time the partial property, you can write mu. The integral Gibbs energy is this sum of the partials, or GA, you replace mu A. Delta G is the, I can write this equation out here, delta G is the partial molar Gibbs energy of mixing, or it's called the relative partial molar Gibbs energy, or the relative chemical potential. So I could say dGi is GI minus G naught I, or it's the same thing, it's equal to d mu I, which is mu I minus mu naught I. It's the chemical potential of the solution of component I in the solution minus the chemical potential of pure component I. And we define that as RT log activity of I. Sorry, that's not actually, let's write it this way, equals RT log activity of I. And somewhere, that is actually a definition of the activity. That is, you should really turn it around if you want to do it right. The activity of I is defined as delta mu as the exponent of mu I minus mu 0 I over RT. That is the actual definition of, proper definition of chemical activity. Okay, in terms of the chemical potentials. Okay, the chemical activity of a component I in a solution is the exponent of the chemical potential of that component in the solution minus the chemical potential of the pure component at the same temperature divided by RT. It's usually written out delta mu I equals RT log activity of I. It's usually written out that way, but that is the definition of activity. Now, since mu I, okay, now we know that mu I is a chemical potential. Okay, so material component I will always go from high potential to low potential, from high mu I to low mu I. So it'll go from high activity to low activity. Activity is just the exponent of the chemical. It's just making it an exponential because it's often more, it's not a new property at all, it's just, it's often more convenient to put it relative to, because mu I again doesn't have a natural zero, so we put it with respect to the pure component at the same temperature, and by putting it as an exponent, you'll see in a minute, makes it mathematically a little bit more convenient. But material, component A will always go from high mu A to low mu A. For the same reason, component A will always go from high activity of A to low activity of A. So we can say when two phases are in equilibrium, every component, the chemical potential of A is the same in both phases. Same for chemical potential of ECD, the activities are all equal. With the activities, you've got to be careful that it's with respect to the same standard state. Okay, because the activity is really a relative property. It doesn't, mu I, it always goes from high mu I to low mu I, but if you define the activities with respect to a different standard state, then of course you might actually get something going from low activity to high activity simply because you haven't got the same standard state. You got to have the same mu naught if you're going to compare activities. Come to that in a minute. So, delta Gi is RT log activity, or this is delta mu I, so delta G is delta G. The integral Gibbs energy of mixing is the weighted sum of the partial Gibbs energies of mixing. And the delta G is the same thing, and this integral, this is delta GA here, this is GB here, the tangent construction, and this is delta GB. Or you can do a delta G mixing, and then this is delta GA mixing, and this is delta G mixing. So it's exactly the same thing as with the V and with the H and with the S, and so on. If we plug this thing here, that G is RT log activity, and we plug that into here, we can then say that delta GA is RT log activity of A, so we get this expression, which is important. Delta G is RT XA log activity of A plus XB log activity of B. Okay, this is a general equation that's always true. Comes from the definitions. Now I said with delta V or delta H, the delta V or delta H, the delta V or delta H could be negative, it could be positive, could be zero. For delta G, however, it has to be negative if in fact you're talking about a stable solution. Remember, delta G is the the integral Gibbs energy of mixing is the delta G for this mixing reaction. If delta G is positive, then they don't mix, they're immiscible. Okay, so to have a miscible solution, delta G has to be positive, negative. Of course, you could have a delta G positive. You could talk about a metastable solution if you want. You have a positive delta G, that would be the metastable G you would get if the solution were formed. But I mean, for a stable solution, delta G of mixing has to be negative. Also, the partial Gibbs energies, delta GA and delta GB, have to be negative. Why is that? Suppose you had a solution. Let's say you had the activity of A was greater than 1. So if the activity of A is greater than 1, that means that mu A is greater than mu A 0. So what happens then, of course, is that A comes out of solution for pure A. Goes from high potential in solution to low potential in the pure component. So the pure component has a lower potential of A than A in solution, so it comes out of solution. So you can't have a solution in which the activity is greater than 1, at least with respect to forming a standard state which is at least accessible, a real standard state. So if we plot delta G, A versus delta GB, as we rotate the tangent around, so now we take the tangent plane and we rotate it around like this. Okay, we see that delta GB is this intercept over here, delta GA is this intercept over here, so it's the same thing as I did with the volume and I did with the heat. The delta GA starts at 0 for pure A, and it decreases down here for pure B. And delta GB starts here and decreases down this way, whereas delta G is this curve here. And delta G then is RT log activity, so RT log activity goes this way. Okay, so again, when you got the pure material, delta G is equal to 0 and the activity is equal to 1. So the activity at this point here, this is pure A, the activity of pure A is equal to 1, and RT log activity of A is equal to 0, so delta G is. And these will always be negative if, in fact, the solution is a stable solution. Meaning stable with admissible solution. Same thing as saying stable. You get that kind of curve. Getting ahead of myself a minute, but now I said with the delta curve of delta V or delta H, I said the intercept over here was finite. So the delta V curve went down to here and had an actual value, a finite value, and delta GA has a finite value in pure B. But what is the activity of A in pure B? 0. Okay, so delta GA then, in pure B, you have log of 0, which is minus infinity. So this curve then goes to minus infinity, and this curve here goes to minus infinity. Unlike delta V and delta H, which don't go to minus infinity, the delta G does. The delta S also goes to infinity. All right. Or which means if you look at it at the delta G curve, if this is the delta G curve, it is not drawn correctly here, but if delta GB, which is the intercept here, is going to go to infinity, what it means is this delta G curve, the slope here is vertical. It isn't drawn right here. This should come in vertically at that point. Delta H curve doesn't. If this was H, the delta H curve doesn't have a... The delta H curve has a finite slope. The delta G curve has an infinite slope.
Must it be symmetrical?
No, not to be. An ideal solution will be symmetrical. Well, and okay, we could write this out for an ideal solution. Wait a minute. For an ideal solution, what do we have for an ideal solution? We can write the ideal solution right now. For an ideal solution, well, maybe we can't write an ideal solution right now. Yeah, okay, let's do. Okay, here we go. Okay, for every solution, the delta G is RT log activity, and the delta G of mixing is delta G AXA plus delta G BXB, which is RT log activity of A. So these equations hold generally for every solution. For an ideal solution, the ideal activity is equal to the mole fraction. Okay, or the activity is equal to the activity coefficient times the mole fraction, but the ideal activity coefficient is equal to 1. So in an ideal solution, the activity is equal to the mole fraction, The ideal Gibbs energy is RT log xi rather than activity-wise, so the ideal Gibbs energy of mixing is RT XA log XA plus RT XB log XB. This is the general case. If you let the activity of A is equal to the mole fraction of A, the activity B the mole fraction of B, then you get the ideal Gibbs energy. Okay, I'm kind of doing this backwards, but I'm sure you've seen it. Delta H ideal is, of course, 0. Okay, so delta G ideal is minus T delta S ideal. Okay, delta G, and this is doing it the right way around. Delta G ideal is defined from here. Delta G ideal is RT XA log activity of A ideal plus XB log activity of B ideal. Okay, and that should be equal to minus T delta S ideal. Okay, but we already showed that delta S ideal is equal to minus R XA log XA plus XB log XB. Okay, this we showed earlier today from the Helmholtz equation. Okay, so that's your ideal entropy. It's minus R XA log XA plus XB log XB. The ideal enthalpy is 0, so the ideal Gibbs energy is minus R. So the ideal, therefore, delta G, I'm doing this totally backward, delta G ideal is RT XA log XA plus XB. Okay, let me do it the right way around. The ideal entropy is given by, do it the right way around. The ideal entropy is given by Helmholtz equation as that. We derive that from S is K log T. Okay, the ideal, so that's the ideal entropy. The ideal enthalpy is 0. So the ideal Gibbs energy is minus T delta S ideal. Therefore, the ideal Gibbs energy is RT XA log XA plus XB log XB. But from the definition, okay, for any solution, delta GA is XA log XA plus XB log XB. Therefore, activity of A ideal equals XA when you compare this to that. Okay, so hence, this is simply from the definition of activity. If we make the assumptions of an ideal solution and use Helmholtz K log T, we end up with this expression for the Gibbs energy of mixing, so it shows that the ideal activity is the mole fraction. Okay, so that's the true definition of the expression of activity, ideal equals mole fraction. And since the ideal activity is equal to the mole fraction, then if you have an ideal solution, again, then you can see if you were to plot an ideal solution, this activity would be the mole fraction, and when the mole fraction goes to 0, the delta G partial goes to minus infinity. Obviously then, in an ideal solution, to answer your question of symmetry, in an ideal solution, of course, is obviously symmetrical. Okay, so in an ideal solution, the delta G is symmetrical, and will have its minimum at 50%. But in a real solution, of course, it does not have to be symmetrical. So in an ideal solution, the activity is the mole fraction. In a real solution, it can deviate from the mole fraction. It can be higher or lower than the mole fraction, depending upon various factors. And so I think that's enough for tomorrow. You can look at the rest of this stuff, these PowerPoints here. And section 4.1 for Thursday. I'm going to continue with this, and I'll be talking about deviations, excess properties, regular solution theory on Thursday, and how you use activities in chemical reactions and so on. So we'll finish the fundamentals of solution theory, and if you want to move ahead of yourself, read section 5 on the binary relation between thermodynamics and binary phase diagrams. Any questions? Now I've got to turn it off.